Hello everyone, this is Sarvesh, lecturer in Civil Engineering, Government Polytechnic, Station 1. The course is Reinforced Concrete Structures. And today, this is a continuation to the previous lecture, that is the design of continuous beams and slabs by limit state method as per IS 456-2000. After completion of this lecture, you are able to know what are the different codal provisions to be followed by using the IS 456-2000 for calculation of effective span and limiting stiffness. And you are able to know about how to determine the bending moment and shear force coefficients and how to determine the maximum shear force and bending moments in continuous beams and slabs. And we will solve some example problems on determination of bending moment and shear force at critical sections by using IS 456-2000 for better understanding. So before going to start, just recap what we were discussed in our last class. In last class, we were discussed about what is the difference between the simply supported slabs and continuous slabs, and what are the difference between the simply supported beams and continuous beams. Then we were discussed about where the and what are the advantages of continuous beams and slabs. As we discussed, the deflections are lesser in continuous beams and slabs as compared to simply supported beams and slabs. And one more thing is the thickness of the continuous beams is higher than the thickness of the simply supported and beams and slabs. And in last class, we were discussed about the how the continuous beams will behave under the application of loads. That means the behavior of the deflection or bending moment diagram of the simply supported beams as well as continuous beams and slabs, right? And today we are going to discuss what are the IS 456-2000 codal provisions and in continuous beams and slabs. For effective span, as per IS 456-2000 class 22.2, if the width of the support is less than the 1/12 of the if the width of the support is less than the 1/12 of the clear span, then the effective span should be calculated from list of these two, right? That means the center to center distance of the supports or clear span plus effective depth, whichever is lesser, right? Suppose, let us say, as shown in last class, if this is the continuous slab, that is continuous beam for the supports. Right, sorry, the width of the support, right? So suppose this is a continuous beam having different. This is a support. That means the beam or slab is resting. This is the width of the support, right? So this width of the support is less than the 1/12 of the clear span. Clear span means the inner to inner distance between the support. This is called as clear span, and this is the width of the support. So before going to use determine the effective span, you need to check whether your width of the support is less than 1/12 of the clear span or not. If it is less than 1/12 of the clear span, you just calculate the effective span by using these two cases and consider the least of these two. That means center to center distance of the supports or effective span plus clear span plus effective length, whichever is lesser. Right? Suppose if the width of the support is greater than 1/12 of the clear span, then how to determine the effective span of the beam? So in that case, you have to determine the, let us clear this. Suppose if the width of the span, width of the support is greater than the width of the 1/12 of the clear span. In that case, the effective span should be calculated like this. If the width of the support, if the supports are wider than 1/12 of the clear span or 600 mm, whichever is less. That means here you need to consider two cases. One is if the uh, width of the support is greater than the 1/12 of the clear span or 600 mm, whichever is lesser. If this is the case, then you need to determine the effective span of a continuous beam from, that is, for end spans in the one end and sorry, end span in one end is free and other continuous. For end spans, suppose we are calculating the effective span for this case, that means end span, one end is free and other end is continuous or intermediate span. For these cases, you need to calculate the effective span is equal to clear span between the support, directly you can take, right? So if this is the case, that means if the width of the support is greater than the 1/12 width of the support is greater than the 1/12 of the clear span or 600 mm, whichever is lesser. In that case, again, in this case, if the span is one end free and other end is continuous or intermediate span, you can directly take effective span is equal to clear span between the support, right? And in another case, that is for end span with one end free and other end continuous. So here it is for end span, uh, for end, sorry, one end free and other end is continuous or indeterminate, for intermediate span. And for this end spans with one end free and other end is, this is fixed, not continuous. One end free and other end continuous, other end is fixed. So in this case, we need to determine the right. So in this case, both are seems to be no, something. Right? Yeah, in this case, it is one end free and other end is one end free and other end is in this case there is a small correction here. Yeah, with the this is fine. If the support is wider than 1/12 of the clear span or 600 mm, whichever is lesser, and in this case, end spans in one end free and other end is I think as per the codal provision, one end is fixed. This is not free. For fixed, for this is uh, fixed and other end is continuous, or for other intermediate spans, the effective span is equal to clear span between the supports. It is already given in your IS code, right? So this is fixed, so not free. Just correct it. And next one is if in this case, in this case, right. So in the same case, if the one end is free and other end is continuous, right? Earlier it is fixed, one end fixed and other end continuous. Now it is one end free and other end is continuous, then the effective span should be calculated by using clear span plus half of the effective depth, or clear span plus half of the width of discontinuous support, and whichever is less. So you just determine the effective span for this case. So effective span, clear span plus half of the effective depth, or clear span plus half of the width of the discontinuous support, right? So whichever is less, that we should take. Right? So here we have discussed three cases. The effective span should be calculated based upon the width of the support. Suppose, for example, if the width of the support is less than the 1/12 of the clear span, then the effective span is same as our simply supported beam, that is center to center distance between the supports, or clear span plus effective depth, whichever is less. If the the width of the support is greater than the 1/12 of the clear span, or 600 mm, whichever is lesser, there are two cases. Then first thing you need to check if you are going to calculate the effective span for end spans in which the one end free, this is correction, right? One end is fixed, this is fixed, and other end is continuous, or for other intermediate spans, the effective span is clear span with the support, right? And next case is if the other one end is free and other end is continuous, the clear effective span is clear span plus half of the effective depth, or clear span plus half of the width of the discontinuous support is earlier. So based upon the criteria, you need to determine the effective length of the span, right? So next is limiting stiffness, right? You need to determine the limiting stiffness of the member. Now coming to the limiting stiffness of span, right? So if for spans up to 10 meters, the span to effective depth ratio should not be exceed 26 into modification factor. That is, as we discussed in previous classes, that means for checking of stiffness or deflection, you need to determine the modification factor, right, based upon the reinforcement provided in tension zone, right? So similarly here also you need to calculate the modification factor based upon the f of s value as well as the percentage of tension reinforcement provided at the mid span, right? So that is as per figure number 4. Right? So here for continuous beams up to span 10 meters, the effective depth ratio should not be exceed 26 into modification factor, right? So right, class 22.5 of IS 2000 gives the simplified coefficients to determine the maximum bending moment and shear forces. See, as we discussed in last class, see, the beams and slabs are constructed monolithically, continuously. We cannot construct one slab one time, another slab one time. No, we will construct at a time continuously, right? So what happens when you apply the load at any part of the span? So there is some effect on other spans also, right? So that is why there is a distribution, right? So when you apply the load in this span, so there is some part of load will transfer to the other span. So there is always some distribution is there because it is a monolithic construction, right? So there are different methods are available to determine the accurate shear forces and bending moment at a given point based upon the distribution method. That we call it the redistribution method, right? So, but as per IS 456-2000, it is giving a simplified method to determine the maximum shear force and bending moments for continuous beams and slabs. But these method, uh, these, the shear forces and bending moments are calculated based upon the coefficients which are provided by the IS 45000, right? And from that coefficients, you can determine the maximum shear force and bending moments. This is bending moments in continuous beams and slabs. But one thing is, this method is approximate method, okay, but it will give the reasonable values, it is accepted. But one thing is, this method is applicable only for uh, some conditions are there. So as per IS 45000, there are some limitations for application of this coefficient. Right? What are those limitations? The limitations for application of this method is, because see, you can determine the shear forces and bending moment based upon other methods also, like moment distribution methods, Carney's methods, or another stiffness method. But this will give the uh, cost as compared to other methods, because for distribution, I hope you already uh, did lot of you already studied about this Carney's method, moment distribution method, or substitute trend methods. So it will take a little bit more time to analyze, right? So this will give the quick solution. But only thing is, there are some limitations for application of this coefficient. The limitations are, first one is, this method is applicable. So, applicable. You need to check minimum number of spans should be 3, right? So this method is applicable for the spans of having minimum 3 numbers. That means, so this is let us say 1 span, 2 span, and 3 span. So this method is applicable for minimum. It should have a 3 span. If it is 2 spans, then this method is not applicable, right? So minimum 3 span should be there. And one more thing is, the loads should be UDL. The load should be acted on this slabs or beams should be UDL. That is also very, very important. If it is a point load, then you need to do for you have to go for another method, right? That means you may go for distribution methods or Carney's method to determine the proportion and bending if it consists of some point. This method is applicable, stated that the minimum number of spans are 3. This method is valid, or limitation. And the beam or slab should consist only the UDL load. That is second. And one more important thing is, see, no span should differ by more than 15% of the longest span. What does it mean? Suppose, let us say, this is your L1, this is your L2, and this is your L3, right? So no span should differ by more than 15% of the longest span. Suppose, let us say, I am assuming that L3 is the longest span, right? And the condition is the difference, that means the differ by more than 15%. The difference between L1 and L2 should not be greater than the 15% of L3, right? This is very, very important. So it should not be greater than 15% of the longest span. I am assuming that L3 is the longest span. So the difference between any span, the difference between any span should not be greater than 15% of the longest span. If it is greater than, this method is not applicable for that beam, right? So this condition is also should be satisfied. So these 3 conditions you should remember before applying this IS 456-2000 method, right? If any of 3 is not satisfied, then this method is not applicable for that case. This is very, very important. You should remember, right? So shall I repeat again? So the three conditions is, first condition is the minimum number of spans should be 3. That means the beam or slab should consist of minimum 3 spans, and it should consist only the UDLs, and the no span should differ by more than 15% of the longest span, right? If these three conditions are satisfied, then you can apply this method, right? If it is if it is not satisfied, then you have to choose another method, right? That is very, very important. And if it is satisfied, then you can calculate the shear forces and bending moment coefficients, which are given in IS 456-2000, table number 12 and table number 13. Table number 12 given the coefficients for the calculation of bending moment, and table number 13 is given for calculation of shear force, right? Next is, so we'll solve some example problems how to determine the maximum bending moment and shear forces for a better understanding. For example, example 1, right? Calculate the maximum bending moment at the support for a continuous beam of effective depth is 350 mm, overall depth is 400 mm, clear span between the supports is 4 meters, width of the beam 230 mm, width of support 230 mm, imposed load, that is not fixed, 8 kilonewton per meter, and imposed load for fixed case 12 kilonewton per meter, which is excluding the self weight of the beam. And the number of spans, is 4 meters. So you need to check whether your whatever the method, that means IS code method, is applicable for this given beam or not. How to check? As I told, 3 criteria. One is it should consist of minimum 3 spans. So how many spans are there? So 4 spans are there. The first condition is satisfied. Second one is it consists of only the UDL load. So what are the type of load here? This is 8 kilonewton per meter. This is 12 kilonewton per meter, excluding self weight. Self weight is also in terms of UDL. So this condition is also satisfied. Next one is the width span difference is not given, so assuming that it is satisfied that condition also, because all spans are 4 meters, right? So it is also satisfied. The difference between difference is 0. So right, because all spans are 4 meters. Now coming to the solution. The first case is you need to determine the effective length of the span. How to determine the effective length of the span? The effective length of the span depends upon the width of the supports of a continuous, right? So as just now I have showed that if the width of the support is less than the 1/12 of the clear span, there is a separate method to determine it. Similarly, if the width of the support is greater than the 1/12 of the width of the support or 100 mm, whichever is lesser, then you have another 2 criteria. That is, the one end is fixed and the other end is continuous, And if another case is if one end is free and other end is continuous, right? So first check whether your width of the support is less than or less than 1/12 of the clear span or not. So here the width of the support I have is width of the support is 30 mm. Then the clear span by 12 is equal to my clear span is 4000 by 12. You will get 333.3 mm, right? Then the width of the support is 230. So 230 is less than the 1/12 of the clear span, right? So in this case, the effective span should be calculated same as above, simply supported beam. That means the center to center distance between the supports or clear span plus effective depth, whichever is less. So here the center to center distance is nothing but suppose this is your beam and this is one support, this is one support, this is one support. Just an example only. This is the one support and this is another support, right? So the center to center distance between the support means from this center to this center, and here also from here, and here also from here. So that means the clear span is 4 meters plus so here the center to center between the supports is 4 plus 0.2 by 0.23 by 2, 0.23 by 2, you will get 4.23 meters. And similarly, clear span plus effective depth, that is 4 plus 0.35, 4.35. So therefore, the least of, you should consider the least of these two. The list of these two. So which one is least? 4.23 meters. So this is my effective length of the stack, right? So next is you need to determine the loads, right? So here we have two loads, that is fixed and not fixed, right? So the self weight is not included, so you need to determine the self weight of the beam. That is the self weight of the beam is 0.23 into overall depth is 0.4 into 1 meter. We will consider 1 meter length and 25 is the unit weight of concrete RC. So you will get 2.3 kilonewton per meter. An imposed load, that is fixed one, 12 kilonewton meter. And therefore this is also fixed because the self weight of the beam is permanent throughout the life of the structure, right? So therefore it is also fixed. So 12 plus 2.3, you will get 14.3 is the total fixed load, that is I can call it as WD, right? An imposed load that is not fixed, it is already given 8 kilonewton per meter. So these are all working loads. You need to determine the factor load. The factor load should be considered by applying the partial safety factor for loads, right? So as per IS 456-2000, the partial safety factors for live loads and dead loads combination is 1.5. So here the for fixed WUD for fixed load, the partial safety factor is 1.5 into 14.3, we will get 21.45 kilonewton per. Similarly, for not fixed, that is WUL, that is 8 into 1.4 into 12 kilometers per meter. So these are the factored load for fixed, for not fixed, right? Next, you need to determine for this loading condition and for effective span, you need to determine the shear force and bending moment at a given point. So, where it is asking to consider at the support for a continuous, right? So, this is a table for determining the moment coefficient, right? So, for bending moment coefficients at support next to the end support. So there are two, as we discussed in last class, there are two types of movements, span movements and support movements. There he is asking to determine at the support moment, right? So that is maximum. So you just calculate the maximum support moments means two support moments will come. That is at support next to the end support, at other interior support. As I told earlier, suppose this is your continuous beam. This is the span, first span, second, third, and fourth. Let's say. The terminology should be understood very clear, therefore it is easy to operate. So let us say this is a beam and this is my first support, second, third, fourth, fifth. So he is asking to determine the maximum support moment. So in support moments, there are two support moments. One is at support next to the end support and at other interior support. So from this diagram, at support next to the end support, that means this is the support. Next to the end support means this. So it will give the bending moment at here, or this is the end for this case. So next to the end support means here. So from here and here, you have to use this coefficient to determine the bending moment at this support and this support. These are the support next to the end support. And again, you need to determine the interior supports. Which one is interior? This is the interior. Why we are discussing only support moments? Because he is asking for only for support moments. He is asking maximum bending moment at support, right? So support moments are two. From these, you need to determine the maximum bending, right? So one method is, what you can do is, you should calculate the bending moments for at support next to the end support by using these coefficients, and you should calculate the bending moment at other interior support by using these coefficients and find out the bending moments and compare these two. Whichever will give the maximum, that is the maximum bending moment at support. That is one method, right? And another thing is, by just observing these factors, you can easily identify which you will get the maximum bending moment. So these are the factors. See, the load in both the cases is same, and the effective span is same. The only changes is only the factors, these factors, right? So from the factors, you can easily identify where you will get the maximum bending moment, right? To save the time. So no need to calculate for all the supports, right? Just by observe the factors, and we can easily identify which will get the maximum. So from this, you can easily identify where you will get the maximum bending moment. This just is a simple calculation. Whichever the factor is higher, there you will get the maximum bending because the load and effective span is constant. The only difference is this factor, right? And here, obviously, at support, you will get the negative bending moment. As I told earlier, for the continuous beams, the bending moment, the deflection or bending moment diagram for this one, it will come like this. So here is 0, so we will write this, then it will come and again write this, come, rise, and it will drop. So this sagging bending moment at mid and hogging bending moment at the support. So hogging is negative. Negative indicates hogging bending. So at support you will get the negative bending, right? So you will get the maximum bending moment at support next to the end support. So no need to calculate. If you have any doubt, you can calculate the bending moment for the next to the end support separately and for other interior supports, and you can compare the values, right? So why you will get maximum here? The factors is this is 1 by 10 and this is 1 by 9 and both are minus. You just add it. Here also same, but here this is 112. This is 110. So obviously here you will get the maximum bit. So for saving time, I am taking directly calculating these factors, right, and calculated the bending moment. So for dead load and imposed load for fixed at support next to the end support, that is 1 by 10. And for imposed load, for not fixed, this is minus 1 by 9. And these factors should be multiplied with load into effective span to determine the maximum bending. See, from 12, maximum support moments occurs at support next to the end support. That from that table you can easily identify. If you have any doubt, you can calculate and you can find it. So here both are negative. So minus 1 by 10 into, this is for fixed, right? WUD into L square minus 1 by 9 WUD into L square. This is for not fixed. This is for fixed, right? So 1 by 10 into 21.5 for this is for fixed load, factor load, and our effective span is 4.23 meters, right? So 1 by 10 into 21.45 into 4.23 square. Similarly, this is 1 by 9 into, for not fixed, it is 12 and span is 10, 4.32 meters. Okay. And both are negative, so you can add it. So you get the negative bending moment, that is 62.24 kilonewton meters. So this is the maximum bending moment occurred at support in a continuous beam as per the given data from table number 12. Right? So like this, you have to determine the maximum bending moment. Right? Similarly, you can determine the shear force also, where you will get the maximum shear force. So for the same data, the maximum for determining the maximum shear force, you need to use the table number 13 as per IS 4. So from this table, you can observe that here it is given different supports, that is at end support, at support next to the end support, at all other interior supports, right? So here also for determining the maximum shear force, you have to calculate the shear force for all these cases, right? And from where you will get the maximum, that will become as your maximum shear force. That is one method. Another is from the table you can observe the values. So as I told just now, where the factors are higher, because here whatever the load for fixed case and not fixed case is same for all these cases, and effective length is same. So these two factors are constant, right? Only thing is the coefficients will change depends upon the support conditions, right? So suppose from the coefficients you can easily observe and identify where you will get the maximum shear. So from this table you can easily identify where you will get the maximum shear force. It is very easy. It is a simple, normal, simple problem, 10 class. Right? So here the factors for fixed is 0.4, this is 0.45. And here there are two, as I explained earlier, that is outsider and insider. So for outsider it is 0.6 and 0.6. For insider is 0.55 and 0.6 for the coefficient for fixed and not fixed. And for all other interior supports, for fixed is 0.5 and for not fixed is 0.6. So tell me where you will get the maximum shear force. Obviously, where the factors are higher. So compared to all values, the factors are higher only in this case, right? So therefore, you will get the maximum shear force at support next to the end support in outer side. So what is outer side? You may have a doubt, right? As I told in earlier class, suppose this is your uh, continuous beam, for example. This is the support next to the end support. So it is a continuous here, right? So this will become as a outer side, this will become as inner side, right? So outer side shear force is higher as compared to all. So therefore, use these bending moment coefficients, sorry, shear force coefficients to determine the maximum shear force. And how to get the shear force? We just take this coefficients and obtain the force. To obtain the shear force, coefficient shall be multiplied by the total design load. So what is the total design load? See, shear force for maximum occurred at outside of the support next to the end support. So VU max equal to 0.6 into fixed load plus 0.6 into, right? So 0.6 into W into L, because this is per meter length, you can multiply with L, you will get the total load. And here also 0.6 into, for the not fixed load, 0.6 into WUL, you will get the total load. So if you substitute the values, that is 0.6 into 21.45 into 4.23 plus 0.6 into 12 into 4.23. So you will get the maximum shear force is 84.9 km. So this is how you need to determine the maximum shear forces at bending moments for a continuous beams and slabs based on the IS 456 method, right? So for this, I would like to conclude this lecture. So before going to close, just summarize what we were discussed till now, right? So today we were discussed about the codal provisions. That means how to determine the effective span and limiting stiffness. So effective span here in continuous beams and slabs should be calculated based upon the width of the support. That means there are if the width of the support is less than or equal to 1/12 of the clear span, then you need to determine the effective span, same as for simply supported beam. That means center to center distance between support, or clear span plus effective depth, whichever is lesser, right? So that is for first case. That means if the width of the support is less than the 1/12 of the clear span. If width of the support is greater than the 1/12 of the clear span or 600 mm, whichever is lesser, Then again there are two criteria. One end is fixed and other end is continuous, or for other interior supports, the effective span is nothing but your shear span. And another case is if the one end is free and other end is continuous, then effective span should be calculated by clear span plus half of the effective depth. And another case, another one is just yeah, clear span plus half of the width of the discontinuous. So uh, whichever is lesser, that should be considered effective span, right? And limiting stiffness for continuous beams and slabs, the L effective by D ratio should not be greater than 26 into modification factor, sorry, right? So that modification factor should be determined from the uh, IS 456-2000 based on the percentage of reinforcement provided in tension zone and F of S value, right? So based upon that, you can determine the modification factor, and that modification factor into 26, you will get the permissible limit, that is L effective by D ratio of the continuous beam. Right? This is what we have discussed, and we have discussed about the what are the different limitations of this method. Right? That is important. What are the limitations? The limitations are whatever the beam you are going to analyze or design, the minimum number of spans is 3. Second one is it should consist only the usual load. And third one is the difference between the spans should not be greater than the 15% of the longest span in the beam. So these three conditions must be satisfied. If it is satisfied, then only this method is applicable. If it is not satisfied, this method is not applicable. You need to go for another. You need to go for another method, right? And we will solve one example problem how to determine the maximum shear force and bending moment, right? Based upon the IS 456 method. That means we have calculated the effective span based upon the thickness of support, and we have calculated the loads, and from that we have calculated the factor loads, and based upon the conditions of the member, and we have calculated the we have bending moment coefficients are taken from table number 12 and calculated the bending moment. And I told that you need to calculate for all the cases. If you have any doubt, you can calculate it and compare and find out the maximum, because here is they are asked to determine only for maximum shear force and bending moment. So from the coefficients, you can easily identify where you will get the maximum uh, bending moment and shear. So that is why I have taken I have calculated directly the maximum bending moment from the coefficient, and similarly I have calculated the maximum shear force from the coefficients itself. You can easily identify which one is the maximum, right? So this is what we were discussed till now. So next class we will discuss